guys. So we have the race car class here today. We also have actually the UAV class. Feel free to move up. You don't actually have to be in your assigned spots for the seminar yet. Get close. Kyle doesn't bite. He's actually really cool.
Despite my appearance.
So Kyle's joining us today from JPL, the Jet Propulsion Laboratory out in California. It's one of NASA's big research areas, and I think he'll give it a much better description here. So I'd like you all to give your attention to Kyle, and also no cell phones.
All right, thanks, Andrew. Good morning, everybody. How are we doing? Good. So as Andrew said, my name's Kyle. I'm a robotics engineer at NASA's Jet Propulsion Lab. NASA's Jet Propulsion Lab, we're one of, I think it's 11 NASA centers, and we're responsible for unmanned exploration of the solar system. That's our charter. So what does that mean? It means robotics. So today, I'm going to talk to you about control systems, and we're going to get into what are control systems, why do we use control systems in robotics, and just sort of some of the basic nuts and bolts. But the other reason that I'm here today is to provide you an opportunity to ask questions about robotics, about careers, about NASA, about space, anything you think you might be able to get from me. And just a disclaimer, I'm biased. I love JPL. I'm very interested in trying to recruit you to come work for us when you graduate, so just bear that in mind. That's also a reason why I'm here. But before we jump into all that, oh, and by the way, so the way this is structured is we're going to talk more technically for the first like 50 minutes, 60 minutes, something like that, and then we're just going to open it up to general Q&A about whatever you want to talk about. That being said, feel free to stop me at any point with any questions. All right, so let's watch a video. And this is something that we're working on right now. Okay, so that is the Mars helicopter, and that is launching as part of the Mars 2020 rover mission, set to launch in, surprise, surprise, 2020. I actually don't work on the helicopter. People in my group do, though, so I'm somewhat familiar with it. What I work on is the control system for the sampling and caching portion of the rover, so big robotic arm, drill, and all the stuff that needs to cache samples, which we're going to go and collect on the Martian surface and then potentially retrieve them back to Earth for analysis here. So with a project like this, where we're trying to fly, and obviously this is, in case it wasn't obvious, this is the first time we'd ever fly something like this on another planet. So what do we think some of the challenges might be with trying to get a helicopter like this to work? Yeah?
The thinner atmosphere?
Yeah, exactly, thinner atmosphere. So what were they doing in that test that we saw? Yeah. Yeah, they put it in a simulated Mars environment. So we have what's called a low-pressure chamber at JPL, so we can use a pump to pump the pressure of the chamber down. Mars' atmosphere is about 1% of Earth's atmosphere. And so what this means is that it's very hard to generate lift compared to the way we generate lift here on Earth when we're talking helicopter dynamics. So what that means is that the blades on that helicopter spin about 10 times as fast as they would on a normal helicopter, and we really, really have to minimize weight. So we need low-weight helicopter. This thing weighs under 4 pounds, and it needs to be very powerful to spin these blades at 3,000 RPM. What do you think another challenge of flying this helicopter on the surface is? Yes?
Less gravity.
That's a very good point. There is less gravity. So Mars gravity is about 0.6 that of Earth. What do you think that means in terms of what we're doing when we're testing here on Earth? What's the problem? Yeah. Yeah, it's hard to accurately simulate it. The other problem is it means this is a highly constrained system. It needs to be very light, and it needs to be very powerful. But it only needs to work in a gravity environment that's 0.6 that of Earth. So what that means is it actually can't really fly on, under Earth gravity the way it will on Mars. And so we have to design very complex offloading systems to offload the extra weight of the helicopter that it feels when it's here on Earth so we can test it flying. Okay, so how about in terms of intelligence on the helicopter? What are some other things we expect we might have to do with a device like this that's flying on another planet? Yeah.
Accurate position mapping.
Yeah, accurate position mapping, and why is that important?
So that the drone knows where it is, where obstacles are, and how to get back to it.
Exactly. So it's fair to say there's probably a reasonable level of autonomy on board that platform, right?
Yes.
Okay. Can we joystick the helicopter from Earth? No. Why can't we do that?
Latency.
Latency, right? What's the latency to Mars? Does anybody know?
30 minutes.
Yeah, it's like, it depends on how far away Mars is from Earth, but it's like around 15 minutes. Show of hands, how many people have played with quadcopters? Okay. What's your interface to the quadcopter? Like when you're controlling it, what are you doing? Are you telling the individual blades how quickly to spin?
No.
No. What are you doing?
Just giving it like a roll pitch.
Yeah, you're giving like a roll pitch, and yeah. Okay. So the reason I mention that is because even if this helicopter were for here on Earth, there would still be what's called a control system running on it. And the reason is that you can't fly, as a human, you cannot fly a quadcopter or a helicopter very well if there isn't a control system running on board. Now, there are helicopter pilots. Of course, they fly helicopters manually, but it's a very labor-intensive job, and it requires a lot of training. They become experts. When we're talking quad rotor, I know this isn't one, but just as an example of something we're all familiar with, quadcopters have 4 blades, and it would be way too much on the human to expect you to be able to control the speeds of those blades. So instead, there's autonomy living on board, i.e. a control system, which is operating the helicopter for you and allowing you to give it higher level instruction. Okay, so that's kind of the motivation for just one example of why we need control systems. Okay, so that being said, who wants to give the best description of what you think a control system does in like one sentence? What is a controller? You can have 2 sentences if that helps. Yes?
Basically, it uses mathematical computations to decrease the error between a target value and the value that the system is currently at.
Right, good answer. So basically, a control system takes your system from somewhere to somewhere else, right? And that could be in physical space, or it could be like a temperature or whatever. Basically, it's saying, I have a state of my system, and it's at some value, and I want to get it to some desired value. Okay, so let's talk a little bit about how control systems fit into robotics in general, and then we will talk specifics of controllers. So when we're talking robotics, autonomy, there's kind of like, in my mind, there's 3 main questions a robot needs to be able to answer if it's going to be autonomous or semi-autonomous. The first is it needs to answer the question, where am I? Now again, this could be in physical space, like your colleague was suggesting on the Martian surface, what's my position? But it could also be other things, like I'm using the term where am I a little loosely. It could mean also like what's the temperature of my motor right now? Is it okay for me to continue operating at the power that I'm at? So this is a problem with something called state estimation. If I'm a robot, what is my current state? That's basically what this is getting at. All right, second is, where am I going? By the way, is this writing okay? Folks in the back, can you see this, or would bigger be better? It's good? Okay. I have terrible eyesight, so I can barely see it here. That's why I was asking. So the second is, where am I going? Okay, so I know where I'm at, but where do I want to go? This is a problem of planning. And when we're talking motion, you'll hear it called motion planning. Okay? And then the third is, okay, suppose I can answer the question, I know where I'm at. I can answer the question, I know where I want to go. I have a plan. The controller says, this is how you're going to get there. So the question that the controller answers is, how do I get there? Okay, so this is controls. And if you look in academia in terms of how robotics is taught, it's quite frequently taught, when we're talking about the autonomy side, less like the hardware side, we frequently break it down into these different subsets. In fact, quite frequently on projects, you'll even divide people by expertise into these boxes. That being said, do you think that, suppose I have a robot and I have some ability to estimate my state, I have some ability to plan where I want to go, and I have some ability to get there using a controller. Do you think there's sort of an interconnectedness between these three things, or can they just be treated separately?
There's an interconnectedness.
Right, there's an interconnectedness. And what makes you say that?
Because the state estimation, they all give inputs and then outputs, so they all have to like flow to each other.
Exactly. That's exactly right. So this estimator is going to give some inputs into the planner. It's also going to give some inputs into the controller. The controller is going to make the robot do something, which is going to feed back into what the estimator thinks and where maybe the robot thinks we need to go. And so that's just a point I want to make up front, is that today we're talking about control systems. But it's important to remember the context of what we're talking about. That you can't really consider a control system when you're talking robotics autonomy without at least thinking about these other components. And if you have a robot that works and you make a change to one of these, it may impact your controller. And so I just want to point that out. Robotics is a very interdisciplinary field that requires looking, when you're talking like a capability, like I want to make a robot be able to walk out that door and then go buy me a Dunkin' Donuts because I really miss Dunkin' Donuts because they don't really have them on the West Coast and I'm from the East Coast. And I wanted to bring it back to me. If I want a robot that could do that, I really need to think about all three of these things in conjunction with each other. Okay, so that's sort of how controls fits into the big picture. So let's talk about controls themselves. By the way, are there any questions on any of that so far? Yes?
So is like one the most basic and then two and then three? So like, if you, I guess, does three depend on two depends on why, or does it go over?
It's a great question, and actually it's a bit of a misnomer that I even numbered them, because the reality is that these are all running all the time, and there isn't really a hierarchy per se. The controller might take input from my state estimation in order to tell the robot what to do. But the moment that it starts to tell the robot what to do, the robot's state changes, so that influences the state estimator. And the same can be said about the planner. So these are really three interwoven connected blocks. Probably not the best way that I pictorially showed it. Okay. All right, so let's talk about control systems. So we said that the point of a controller is to take the state of your system from some value to some desired value. That's basically what it comes down to. And the state of my system could be the speed of my vehicle. It could be the attitude of my quadcopter. It could be the force that I'm interacting with the environment with. It can be a whole bunch of different things. To talk about controls, we often express that in something called block diagram form, and that's what I'm going to show you. So one of the things that I'm going to try to communicate throughout this lecture is I'm going to use terminology and I'm going to use diagrams that are used widely in the academia of controls. Because controls is a field that you can get a PhD in. We're going to talk about like one or two different types of controllers. You can get a PhD just in like one kind of control. Like just as an example of like how deep this field goes, we have 50 minutes. So what I want to do is just try to expose you to some of the terminology and the diagrams that you're going to see. So if you go out looking for information on control systems, it won't be the first time you saw it. Sometimes it's just like a translation that has to happen between the question you're trying to answer and how the controls field talks about control systems. All right, so that being said, when we talk about control systems, like I said, we often draw things pictorially in block diagram form. So imagine this block is my system. And my system can take in some input or set of inputs, and the common variable used to express this in controls land is a U. I don't know why. An I for input would probably make more sense, but go figure. The system has some output that's typically expressed Y. The whole goal of the controller is to manipulate this input to get this value to some desired value. So like in your wall following example, if you want to keep some distance from the wall, what's my input? What's the input to the system? Okay. Treating the system just as the robotic vehicle itself. What is it that you have the ability to manipulate in order to get your output to some desired value? Yeah, the steering. Yeah, the steering. That's what I was getting at. So in your example, that you would be the steering, and then what's Y?
The desired steering position.
The actual position. So if this is my car, then this here would be my steering, and this would be my distance. Okay. The term system can be a little bit confusing, and I think that's what's coming up right now, is that when we talk about this part, the way controls land refers to this as the plant. And so instead of seeing the word system, what you'll see is plant. The plant is the thing you're trying to control. You control the plant with the controller. By the way, does anyone know why control systems refers to the thing under control as the plant? It's like a little trivia fact. Okay, it's because the control systems dates back to when chemical engineering processes were being developed. And so the thing they were trying to control was literally like a physical plant, like a plant that produces a chemical. That's where control systems started to come from. So that's why it's called the plant, and it's stuck. Okay. So I have my plant. I have some input at my disposal, and I'm trying to get my output to some value. So when we do that, when we're talking controls, there's two basically big branches of ways you can do this. One is called open loop, and the other is called closed loop. And I'll draw the diagram, and then we'll just walk through what the differences mean. So in the open loop case, I have some block which represents my controller. My controller is computing an input to my plant. And my plant has some output Y. Okay? In the case of closed loop, I have my controller. It computes a U. The U goes into my plant, produces an output Y. All right, what's the big difference with closed loop for those that have seen this before? Takes the output and routes it back in. So this is the most common way you'll see this, is you tap the output, and then I forgot to draw a key variable here. This one is R. So typically we have what's called a reference. This letter actually does make sense, R for reference. So it's where I want my output to be. So based on my reference, my controller does some stuff. It comes up with an input to my plant, and then hopefully I get that in my output. When we're talking closed loop, I also pass in a reference, but the key distinction is I take my output, and the most common thing you would do with it is subtract it from my reference, and this computes what's called an error signal, and this is what you guys were talking about earlier. And the error signal is what gets fed into my controller. So the error is the difference between where I want to be and where I am right now. I feed that into my controller, and my controller tells me how to get there. It tells me exactly what I need to do with the steering in my vehicle in order to get my distance to the wall to be some value. Okay, so open loop, it just takes the input and computes, or it takes the reference and computes some input to my plant. If I'm off on Y, do I have any way of knowing that with an open loop controller? No. So what do you think the more commonly used control type is?
Closed
Closed loop, right? And how do I do this? How do I know what my output is? Sensor reading, exactly. So I take a sensor reading. So there's another box here. And that word says estimator, where I draw this to really make a point about what we're doing when we're running this output back. Okay, so I've got a sensor. What's the sensor for your robotic car? The LiDAR. Okay, the LiDAR gives you what? How does the LiDAR work?
Basically, it just uses light rays to determine the position of objects relative to the sensor.
Yeah, exactly. So let me ask you this. Do you think it gives you a perfectly accurate measurement?
No.
No. If you plotted it versus time, would you expect to see it kind of fluctuate? Even if the car was stationary? Yeah, okay. That might seem like not a big deal, but it's a really big deal. Because the cost of the sensor determines what that band is going to be. So like our iPhone's a great example. Our iPhone has an accelerometer in it. It measures how quickly I'm moving it around. And you can't just put a military-grade accelerometer in the phone in order to get a really good estimate so when you're playing Pokemon Go or whatever, it knows exactly where you are. You can't do that because it's so expensive, they'd never be able to sell an iPhone. So instead, they hire a bunch of really smart people like you that take sensor information from these cheaper sensors that don't provide perfect estimates, and they run them through an estimator block so that they can produce a better estimate of where the phone actually is. So the reason I point that out is because when we're talking controllers, again, the interconnectedness, where am I? This is never perfect, never. And you can't expect it to be perfect when you're designing this controller. If you do, it won't work. You have to be able to account for the fact that this measurement here, despite how good the estimator may or may not be, is not going to be exactly the distance to the wall. It's going to be off a little bit. And that little bit can really matter in certain applications. Okay. All right, so are there any questions on those concepts? Okay. Oh, yes.
Wait, what applications does open loop have?
Yeah, great example. Okay, so yeah, great question. Here's a very boring example. You go to the supermarket and you buy a bag of frozen broccoli. That's your plan. And on the back of the bag, it says, heat this broccoli in your microwave oven for 5 minutes to achieve the desired temperature. That's an open loop controller. Why is it open loop? Because someone at the broccoli company has figured out that basically if you microwave it for about 5 minutes, you get this temperature. So that means what the controller is really doing is it's saying, I want this temperature, I kind of know my plant, 5 minutes. What's the problem with that, though? Yes? Yeah, not all broccoli is the same, right? I'm pretty sure it grows. It's not something we can produce consistent properties of. The other problem is your microwaves are different, right? And sometimes you'll see the bag account for that. It'll say, like, if you have this powerful microwave, then microwave for this long, this powerful, this long. That can all live inside that's all part of the controller. And that's totally fine for that application. And the reason, why is it that we have to do that? Why isn't the microwave a closed loop system? Yes?
Because it would be way too expensive to try and figure out something that could accurately calculate the temperature of the broccoli and adjust the microwave as such.
Yep, you got it. So everyone hear what your colleague said. So it would be way too expensive to try to design a microwave that could also estimate the temperature of the broccoli. You could do it. I'm sure you could do it, but no one would buy it because it'd be like $1,000, and you would say, forget it. If the broccoli's cold, I'm going to microwave it another minute, right? I'm going to manually. and then what are we really doing? We're introducing a controller, right? Because I'm going to pull the broccoli out. I'm going to measure it, and I'm going to say, no, that's too cold. And I'm going to go back, and I'm going to say, 1 more minute. So actually, in that sense, it's a closed loop controller. Okay, yeah, great question. Yes? I'm sorry, I missed the question. Sure.
To know like the sensor readings where they are before putting an input to determine where it goes.
Yeah, that's a great question. So I think if I understand the question right, and correct me if I don't, the question is, why would we start this process of putting an input into my plant before I've even taken a measurement to know where I am? Is that kind of, yeah, so, okay, great question. So first of all, one thing to note is that these controllers, these are running at some frequency. So typically, the way this would be implemented in code is like a for or a while loop or something like that, where the controller is constantly updating this, and this estimation and measurement is constantly happening. It's more like the two are happening in parallel as opposed to this happens and then this happens. They're happening effectively simultaneously. But to your point, typically it's very common in robotics when you boot a system that it has to go through some sort of initialization process like you're describing. You may even have to manually tell it some information like your current heading is this many degrees. And that sort of lives, it would be to the left of all of this. That would happen before we started up this process so that we would get a good first input into the plant, if that answers the question. Yeah, yeah, great question, yes. Would that eventually go into the, yes, it could absolutely affect the reference. So suppose that, let me think of an example. Yeah, okay, so here's an example. Suppose I've got a robot and I don't know which way it's pointing, which is actually a very common problem. Because does anyone know, how do we know when you turn a robot on, which way is the robot facing? A compass, yeah. But what's the problem with the compass? It can get interference. It gets interference from electromechanical interference. What do we typically use on robots to make them move around? Like, what goes in their joints? Yeah, motors. Motors produce a lot of interference. So it's just kind of this catch-22. It's like, yeah, I got a good compass in my robot, but literally the moment I turn it on, that measurement goes to crap. Very common problem. Now, I can pay a lot more to get a good compass that's robust to that, but that's more money. And if I'm trying to mass manufacture a product, that may not be feasible, or it literally may not exist that there's a sensor good enough for what I'm trying to do. So to your question about could that initialization process affect the reference, it could, in that suppose I boot my robot, and it doesn't at first know where it's pointing, and I want it to walk that direction. Then I could boot it and say, I'm going to tell you that the first thing I want you to do is turn whatever that is, 60 degrees, because I took an external measurement, and I know that's the angle you need to achieve in order to get down that stairwell. And so then I could punch in, or the first reference may be 60 degrees. Yes? Yeah, really good question. You can account for that interference in the controller. And a lot of control design has to do with what to do about the fact that this measurement here is what we'd call noisy, where when you plot it versus time, it's got a bunch of fluctuations in it coming from all kinds of interference, quantization, whatever, all kinds of stuff. You can take that into account in the controller directly. The problem is it requires a good understanding of what you think that signal is going to look like. You have to know kind of how is it bounded, how is it shaped, like this interference, what frequency is it happening at? And you may or may not be able to find a controller that enables you to account for it and still produce desired performance at the output. It depends on the application. Yes?
So could the estimator then, and then even for the reference, maybe be filtering that data to come up with sort of smoother input?
Yep, you got it. So suppose this is time, and this is my, I'm going to call it theta for the angle of the compass, right, the compass heading. And maybe this is, maybe the compass heading is fine until I boot the robot, and then I get all this interference, and then what happens is it starts to look like this. And now my robot's moving, and so maybe it kind of goes like this. So you can filter this data, and you can get an estimate of it, and say, well, I'm going to take some sort of time average, and I'm going to make it look like this. Okay, so that seems pretty good, right? We can get a smooth signal out of a noisy one. Two problems with this, though, that sometimes you run into. So first of all, we do this a lot, yes. in answer to your question. Yes, we absolutely do this. We do filtering, and that filter typically lives in the state estimator. Because effectively what it's saying is, I know this isn't really my output of my plant. This is my output plus some stuff I want to get rid of, and so my estimator is going to be a filter to try to get rid of that, so that when I feed it into my controller is happy. There's two problems, though. When you boot the robot, two things can happen. The first is you can get this high frequency and what we call zero mean noise, meaning all it is a signal sitting on top of the real signal. But the other kind you can get is what's called a bias, where you actually end up shifting the whole curve up or down. And that you can't get rid of with a filter necessarily, not the kind that just removes noise. The other problem is this introduces something called lag into your system. So in order to get this smooth estimate, I have to wait a period of time and collect some of these samples and then compute average values as I move along. And there's many ways to do that filtering process, but all of them introduce lag. Lag in the controller, or lag in the estimator, means that now my controller is operating off information that's effectively slightly stale. And that can introduce problems when it comes to hooking the controller up at the plant, because the controller doesn't know that. So anyways, these are all excellent questions, and they get at the heart of why designing this controller is so interconnected with things like the state estimator, and why it's not as simple as just, can't we just design a controller and then slap whatever sensor we want on the robot and expect it to work? No, you really have to put some thought into designing that box. Okay, these are great questions. Are there any others before we move on? Yes?
Would you ever be able to like implement a closed loop within your closed loop that comes with an error with the error?
Yeah, another excellent question. Yes, and I'll give you a real example of that. So the question was about interconnectedness of controllers. Can you have a controller inside a controller? The answer is yes. And we do that actually it's one of the things that I work on for the next Mars rover does that. So just real quick aside, one of the things I work on for the rover is the coring tool, which is a drill that drills into the rock. Well, the coring drill sits on a feed actuator that allows us to move it up and down. And what we want to do is maintain a constant force on the tip of the bit while we're drilling the rock. Imagine if you're using a power drill, like you push on it into the wall, right? We're trying to create a controller that does that. So that's one of the things I work on. That controller, the way it works is there's a force sensor in between the drill and the feed, so we can estimate what the force is on the bit. I take that measured force, I filter it, I feed it into a controller. The controller takes in a reference of the force I want on my bit, my estimate of my bit force, computes an error, feeds it into my controller. But what that controller is spitting out is where I want the feed to go. And where I want the feed to go is yet another controller, which is what we call a closed loop position controller, where all that controller's little world does is it takes in a position and it computes a current to the motor that it needs to apply in order to get the motor to your desired current. So sort of long-winded answer, but yes, you can have interconnected controllers to try to account for some of these errors. And then when you do that, you have to consider both controllers simultaneously when you're doing your analysis. Okay, any other questions before we talk a little bit more about controllers in detail? Yes?
So you know how with like noise canceling headphones, it cancels out the interference, like the noise you don't want to hear?
Right.
The opposite, like, sorry.
Yes.
Is it possible like to do that with this so you don't get the interference like?
Yeah, great question. So the question was about noise canceling headphones, which have a microphone inside of them, and then they actually actuate the speakers the exact opposite of what it's measuring in order to cancel out some frequencies. Right, so the colleague's question is, can you do that with a controller? The answer is yes. You can, but with limitations. And you're going to hear me say that a lot, because there's never a universal, like, yes, we could always do that. And here's why. It comes down to something called frequency. So back to this noise example. It's hard to cancel something like this out. Suppose this were happening in my output, and now I want to compensate for it in my controller input. This is happening at such a high rate that even if I were to change my input at that frequency, but opposite to try to cancel it, my plant won't really respond quickly enough for that to happen. So you can imagine steering in your car, in the RC car, right? If you turn the wheels back and forth, try to turn them back and forth super quickly, like eventually it just won't be able to respond anymore because it just can't do that. It can't actuate the system quickly enough to pull that off. So depending on the frequency content, you may or may not be able to cancel out what you're talking about. But yeah, absolutely, that is something that we look at quite a bit. Another example may be, it's not sensor noise, but there's one more thing which can act on here, which is called D for disturbance. A disturbance is like an external force or something pushing on my plant that's changing my output, and I have no way of sensing it directly. But if I know something about what my disturbance is, I can cancel it out with my input, just like you're asking. Yes?
Back to the controller and have to account for that.
You can, and the trick here is that, so the trick with the disturbances, let me think of a good example. Okay, cruise control in your car. So a car driving down the freeway, and a gust of wind comes, and it blows on your car. So, well, actually, let me back up. We're familiar with cruise control, right? You set, you set a desired speed in your car, and then, so what's the output of my system that I care about? The speed, yeah. What's the input to the system, or to the plant? Throttle, yeah, throttle. So throttle affects what? It affects fuel into the engine, which turns it to acceleration. So in that example, there's a closed loop controller called proportional integral derivative controller, which is the next thing we're going to chat about, which is one of the most widely used closed loop controllers in all of industry. Actually, it's not one of, it is the most used. It's probably 90 to 95%, I would say, of the closed loop controllers running in the real world are PID control, and we'll talk about why that's the case. Anyways, that was just for some context. So the question about the disturbance is, so suppose in this example, my plant is my car, or in my case, a very old pickup truck, and I have a PID controller, which is, I'm taking in some estimate of my velocity, and I've got some target velocity, and then I'm computing a throttle angle to my engine. And here comes a disturbance, which is a big gust of wind. So a big gust of wind blows towards the car, say, and it slows it down, right? Well, my controller didn't really know that that was coming, and so it does its best to compensate for it, but it's not going to be perfect. You're going to feel the vehicle slow down. So the question is, what if I knew about the disturbance, though? And the problem with that is you may or may not be able to measure it. So for wind, you probably could, right? You could probably put a sensor on there that can measure wind, and it could say, oh, I feel a gust of wind coming. I'm going to increase my input in order to compensate for that disturbance. Could happen. Another way to do it is you could say, with my estimator here, I'm going to play some clever tricks where effectively, if I have a pretty good physics model of my truck, I should know, based on the speed and the input I'm applying, I can kind of estimate if there's a disturbance acting on me or not. So it doesn't really matter what that means, but basically, you can play tricks with your estimator to try to back out what the disturbance was, and then you can compensate for it in your controller. So it's another way to do it, without measuring directly what the disturbance was. Yes?
But you need to measure it at all because the estimator calculated the error.
Yeah, right. So this comes down to controller performance. So, oh, and by the way, the class last year noticed this, that I have this horrible habit of rolling chalk in my hand, and I have a ring. And so it creates dust, and then it goes all over this nice black shirt that Lisa gave me. So just sort of point that out. If you find it funny, like I find it kind of funny, that I'm just going to get covered in chalk throughout this lecture. So hopefully that's cool. All right. So, yeah, and by the way, this is part of the reason why I'm here, is to try to answer some of these questions. There are details of like PID controller we're not going to have time to get into today. That's okay, because there are plenty of people that can talk to you about that stuff. I'm trying to provide some sort of like real-world experience in what my struggles and successes have been implementing this stuff in applications at NASA and other places. Okay, so the question was, why do I need to estimate disturbance? Because I'm going to see that show up as error in my controller, and then I'm just going to respond anyways. It's true, but suppose this is time. Suppose this is my desired velocity of my car, 70 miles an hour. And suppose I'm cruising along and let's just say I'm tracking perfectly. So I have zero error because I'm totally at my target of 70. Okay, along comes a gust of wind, disturbance. What happens? It'll slow down, right? And then what does the controller see? It sees an error, so what does it do to the input? Increases it, right? So what happens to my speed? It goes back up, right? Okay. So that's kind of what would happen. And then the question is this a problem or not? No. Okay, why'd you say no?
Because it accounted for the disturbance.
Right, account for the disturbance. Okay. Suppose we're talking about a similar problem. Suppose we're talking about a similar problem, but I'm talking about, say, like position control of a robot manipulating silicon wafers. And a disturbance comes along, and it won't be in the form of a gust of wind, but something else, like, I don't know, I can't think of anything clever off the top of my head, but something. Something perturbs the robotic arm a little bit. And we're doing this very tight manufacturing process. Now, does something like this become an issue? It can, right? So really what it comes down to, and again, back to the theme of like, there's no universal, really good answer. It totally depends on your application. It all comes down to what do you need your controller really to do? So if I'm a human, and suppose this means I dip down to 68 miles an hour, it's like, who cares, right? So that's fine. So I don't need to spend the time to try to estimate that disturbance because that's just money it doesn't need to get spent. It's engineering brain power. It doesn't have to happen for this application. But for other applications, this could be critical that this does not happen. And you can have very tight performance requirements on what that needs to be. And so then you have to do a bunch of analysis and show that in the presence of expected disturbances, we will never get an error beyond some range that's allowed. Okay. Any other questions? Yes.
There are like certain scenarios in which the disturbance of that back the course of the entire phase of that mission, for example. So for example, a re-entry window, a slight disturbance could create a large difference in error in the angle that you actually want to enter the Earth's atmosphere, and that can result in you going shallow or just going too far in. So is it possible to create a controller that will actually account for not like possible scenarios, but like possible ways of actually accounting for that error asset in the future before it even gets to that phase. So not exactly real time, but kind of real time. So it takes in that disturbance and then processes like what various scenarios on how to account for that.
Yeah, good question. So colleagues discussing the idea of how you could account for this disturbances in situations where it really matters, like re-entry into Earth orbit. Or another one is like trajectory control when we fly to Mars. Mars is 250 million kilometers away. And so if we're off slightly in our initial angle as we're cruising over to Mars, that propagates into a huge, huge error when we're out at the planet. And so it's really important that we have very good guidance, navigation, and control that takes us on our perfectly pre-programmed arc to the planet. So the question is like, could you account for this disturbance ahead of time, right? And basically that comes down to, do you know something about the disturbance or not? And if the answer is yes, I know that this disturbance is coming, then yes, you can incorporate the disturbance into your controller and you can try to compensate for it before you ever even see it show up as an error. Yeah, very good questions. Okay, so in the last 10 minutes or so, let's chat about PID control. How many people, before I said the letters, had heard of PID control before? Yeah, okay. How many people think they understand PID control pretty well? Okay, does someone want to take a crack at just what is PID control? Yes?
Position integral derivative.
Great, so that is what the letters stand for, so let's write that down. Okay, it's PID, proportional integral derivative. The three letters in these three words stand for the three main components of the controller. So again, what's the controller? First off, we're talking PID, that means we're talking closed loop. So this is the first closed loop controller that we're looking at. Well, actually, I think you guys looked at another one earlier today, but it's the first one that we discussed here. So the PID controller lives in here, takes in some error, it does some stuff related to these three terms, and then it spits out an input into my plant. Okay, so what I'm going to do is I'm going to write down the math equation for what this plant input U is as a function of my error given a PID control law. And then we'll just discuss what the three different terms are doing. All right, so what this means is, first off, U is a function of my error, right? And U equals some number, which is typically referred to as KP, times my error, plus another number called KI, times the integral of my error, we'll talk about that, plus a third one, KD, which stands for the derivative gain, and this is times the derivative of my error. Okay, and we'll talk about that too. Okay, how many people have seen this equation before? Okay, how many people have implemented this? Okay. Does anyone who's implemented it want to chat very briefly about what your experience was implementing the controller? Yes?
So, normally the way, well, what do you mean, like how I implemented it, or?
Well, what did you implement it on? Let's say that. How did you actually implement the controller? Like was it code or, and then, yeah, what did you learn from trying to do this?
So I implemented it on a drive for an FRC robot, so it's just a big drive train, and I use it as a position controller, so I had to encode it, do it, and I programmed that in to just loop through, and it would look for the error. And then as far as the hardest part for me was the tuning process. And so it was figuring out, setting out my proportional and then figuring out how to integrate the two others.
Yeah, okay, great. Okay, so as your colleague said, he did it for a position control system for a first robotics robot. And as you also said, the hardest part was the tuning, right? Okay, so basically, there's all kinds of control systems out there. So like if you just Google controllers, you'll find thousands of articles about all different things you can put into that box, and that's what you can get PhDs in. Like sliding mode control, which is what my master's is in, or model predictive control, which is really popular right now for autonomous driving. State feedback control, there's just LQR, there's so many different ways of trying to solve this problem. And they all have their pros and cons. Okay, so PID is the simplest mathematical, one of the simplest mathematical closed-loop controllers there is. Because this is it. So what it's saying is the input to my plant is just some number times my error, plus another number times the integral of my error. Integral of my error, what is that? Accumulated error. So it means all of my past error added up together. That's what the integral means. So if you haven't taken calculus yet, it's something you'll learn about when you learn about integrals and derivatives. But basically what this is saying is, this is my error right now, and I'm going to multiply it by gain. This is all the errors I've ever had, every time I've ran my controller, stacked up, and I'm going to multiply those by gain. The third term is I'm going to multiply by my derivative. And so, yeah?
So the integral would
Yes, that's true. We'll get there in 1 second. Okay, so the derivative term.
That's like the error, predicted error, basically.
Predicted error, and why is that?
So because you get the derivative of it, and then you can predict how much error you're going to get in the next time step.
Right, okay. So, and what's derivative?
It's basically the slope of any given point in time.
Right, slope. So derivative, yes.
It's the change in error.
The change in error, right, exactly, yep. So what this is doing, this part of my controller is looking at the current. This part here is looking at the past. And this is trying to look at the future. So I'm going to put it in quotes. Okay, so just 1 second, and then I'll get to your question. So the proportional term is saying, I'm just looking at my error right now, and I'm going to compute an input to my plant based on that. This is looking at what are all my past errors, and then it multiplies that by gain. And then this one is saying, I'm looking at estimate of my future error. And as a colleague was saying, the reason it's future is because this derivative term means how quickly is my error changing. So you can imagine if I know how quickly my error is changing, then I can kind of say, I think this is what my error is going to be in a short time window ahead of me. I think if it's changing this many times, my error is something per second, then my guess is my error, the next time step is going to be this value. And so these three gains get implemented here. And they compute the U to the plant. Okay, there's a question?
Two things. Where's the K stand for?
Yeah, okay, so K is just like the other variables and controls. It doesn't stand for anything. But what these numbers are is these are called gains. And they are fixed, well, they are numbers that you as the controls designer gets to pick when you're implementing this. So you have control over these three numbers. Does that answer the question?
I don't really get what these are.
Right, so, yeah. Basically what these are is, let's look at just the proportional term. So, and we'll look at the cruise control example again here. Okay, so all right, suppose I have a car and it's at 0 miles an hour right now, and I want to get it to 70 miles an hour. The question of controls is, how much throttle and at what times do I apply it in order to get to 70 miles an hour? So one option would be, oh, I want to go from 0 to 70. I'm going to put my foot all the way down on the gas. And then what you would look like is this, where it'd just be some max value. What would happen to my car's speed? It would increase a lot, right? Really quickly. It would be like, probably be very uncomfortable for the driver. I would also get something called overshoot, where I would probably shoot past my target speed, realize I'd done that, take my foot off the gas, and then come back down like this. It would not be a great controller. You can do it in some applications. What PID control is trying to do, and what these numbers are doing, is it's trying to shape this U in a little bit more of an intelligent way. So what it's saying is, I'm going to take my error, which right now is 70, and I'm going to multiply it by some number. Let's ignore this part for right now. I'm going to take 70, I'm going to multiply it by some number, and that's going to compute the throttle angle that I should apply. So maybe that number's here. Okay, so it applies that throttle for a period of time. The car starts to speed up. Now, what happens to my error? It decreased a little bit, right? So what happens to my U? It goes down. And so what you end up getting is a more gentle rise to your target. That's the goal. As I march along, I'm constantly resampling and measuring what my error is and multiplying it by some number to compute what my new throttle angle should be. Now the trick is, these two numbers are here because they effectively, and we won't have a ton of time to get into the details of it, but effectively they help shape this to make it do what you want it to do. It gives you more knobs over how to shape this input. Does that answer your question? Yes?
So PAD is finding more errors in a set amount of time, and then so that the control can respond faster and better way.
Could you say that again?
Like, it's so like the plant will have so like it's registering more errors,
Right.
and then once you have that amount of errors, then the controls will like respond to those errors in a most efficient way.
Yes, that's basically the idea. So, right. So the plant's not doing exactly what you want, right? It's, I want 70 miles an hour and I'm getting 60. So that error is coming back into my controller. My PID is saying, oh, I have 10 miles an hour of error here, plus I have all this past error, plus I think my error at the next time step's going to be this. So I'm going to compute a new throttle angle. I'm going to stuff it in. And then I'm going to see, OK, what is my error now? And I'm going to go back to my controller, and I'm going to keep marching through. And the goal is to drive that error to 0. Yes?
So I can understand how it computes the current patch error. How does it compute the future error?
Yeah, so that's why it's in quotes. It can't. So we don't know what's coming in the future. So it's an estimate. So the way it does that is, there's several ways. But effectively, if I were to plot my error versus time, let's say my error is like this, okay, just as an example. And this is getting a little bit into like what it means to differentiate, which if you haven't seen calculus yet, it's not necessarily super clear. So if this is, suppose this were my error as a function of time, the derivative of that error is the slope. So the rate at which it's increasing over the distance. All right, so what would my derivative plot look like in this case? Constant, yeah. Okay, so the way it's predicting future error is, imagine I'm at this time right now. My controller's saying, well, I know my rate of change of error is this. What do I think my error is going to be at this time step? Well, I'm just going to take my derivative term and sort of extrapolate it out and add it. Does that make sense? So it gives you some indication, because you're estimating how quickly this is changing, it gives you some estimation of where things are going. Yes?
You say that us as like the human controller kind of we choose the
Gains. Will they also change depending on the error?
They can, but typically, in the most simple form, no. So the question was, do these gains change based on the error? And the simple answer is that in most cases, they do not. They're fixed. For some cases, so what does that mean? It means that, first off, how do we implement this controller? Code, yeah, right. Code's the most common. Can you implement a controller with electronics like this? Yeah, actually you can. And actually the advantage is you can run it. Software can only run so fast. Electronics runs at an infinite frequency. So that's kind of the advantage. You can also implement them mechanically. Like for those of you that work on old cars, like carburetors are an example of a closed loop controller that's mechanical. Kind of interesting. So I think the best way to say this. So when you implement this controller, the process that you'll typically go through is you'll write out this code, and then you'll say, oh, but I don't know what to put for those 3 numbers. And that's where the tuning process comes in, where it's up to you, based on what you want your output response to be, to pick those 3 numbers. And most commonly, they're fixed. So if you have like a software system where you can parameterize them, that's ideal. so you don't have to recompile every time you change these numbers. That way you can just quickly change them and see what happens. So the last thing I'm going to mention to you before we just move into the general Q&A, and any other questions there might be, is I'm just going to write down a real cookbook recipe for how you can pick these 3 numbers. Okay, so, and like I said, nothing's universal, right? So this doesn't always work. And I've ran into cases where it doesn't, but most of the time it does. All right, so this would be the process, is you have your plant, you have your computer, you have some sensor, it's giving you feedback estimate, right? You type out this code into C, which if it's not obvious how to do that, there is a bunch of pseudocode online, plus obviously all your staff here can help you figure that process out. But effectively, you translate this equation into code, all right? Then the last step is, well, what the heck do I put in for these numbers? I have absolutely no idea. That bald guy was talking for an hour, and I still don't understand what I'm supposed to put into that equation, right? So we'll cover that. But basically, that's the magic sauce of the PID controller, is what to put into those 3 numbers. And you can spend a long time trying to figure it out. So here's basically the cookbook. Start with KP only. Okay? So shut these terms off, because they'll probably just confuse your life at the beginning. At least that's been my experience. So you start with KP only, and increase KP until you see a response. What do I mean by response? What I mean is, suppose your car's next to the wall, and you're looking at, is my steering change as I say grab my car and move it back and forth across the wall, right? It should change my error, it should be changing my input. So bump this gain up until you start to see the system respond, or the plant respond, okay? And then you can increase further until you see something called oscillation. Have people seen oscillation before in a control system? Yeah, if you've tuned one, you've probably seen it. What does it look like? It looks like something like this, where suppose this is my desired distance from the wall, D desired. An oscillatory controller takes you to the target, but then it does this. Really, really common in controls. Super annoying. How do you get rid of it? You can get rid of it with your friend KD. KD is looking at the rate of change of error. KP, all it cares about is what's this value. KD is looking at what's the rate of my change. And so 2 is add KD to reduce oscillation. Okay? And it's the same kind of thing. So you have a KP, you start bumping it up, you start to see your system respond, maybe it starts to oscillate. Start bumping this guy up, you're going to see this oscillation. Ideally, it'll start to die down. It'll look something more like that. 1 second, and then I'll get to your question. You look like you really want to ask it, so go ahead. Yeah, the KD is operating on this guy, the derivative. Oh, this one? Yeah, okay, so this, what I was showing is that sensor measurements always have noise in them. And that's the problem with this term, is that when you try to do this differentiation, this is going to increase a lot of that noise, unfortunately. So if you take a sensor like this and you run it through the derivative, you'll get a bunch of noise out, which is why your KD term can't be very big. Okay. All right, so you can bump KD up to reduce your oscillation, but sensor noise feeds in here quite a bit, so you can only go so high. And then the last step is add in KI. To get rid of something called steady state error. Okay? And steady state error is something that looks like this. Suppose, I'm just gonna redraw this. I have my D-desired. I turn my car on, I tell it to go to D-desired, it looks something like this. And it's like, oh, that's great. You know, it looks wonderful, except I have this constant offset. What's up with that? Well, that has to do with that D term, disturbance. And you can eliminate this to a certain extent by adding in Ki, which is always looking at the summation of all of this. So it's penalizing this constant offset. And when you add it in, you'll get something like that. Okay, so here's the last thing I'm going to say before we just open this up, is that controls is a confusing topic, okay? Like when I took my first controls course, I had no idea what was going on. Hated it. I absolutely hated it. There's a lot of math, there's a lot of stuff like this, and I was like, I don't understand what we're doing here. And the reason I think I didn't understand what we were doing is that this equation doesn't tell you the full story. That's the problem. This equation tells you what your controller is doing. But the problem is you're connecting your controller to a plant. Well, what's your plant? It could be anything, right? It could be a chemical process. It could be this RC car. It could be a quadcopter. It could be a helicopter on Mars. It could be the force controller I'm writing for the drill. The plant has a huge effect on what's going to happen when I couple a PID controller. And you have to be able to understand what that intercoupling is. The reason we're not doing that a lot here right now is because you have to take at least 2 controls courses in order to really get to the heart of that. Because you have to be able to what's called model your plant. You have to be able to come up with mathematical equations for this so you know exactly what's going to happen when you hook this thing up. And that is not simple. So I just want to point that out. If you're feeling confused, please ask me questions. But also don't feel like, oh, I guess there's something wrong with me, I don't get this. Because that's how I felt, and it turned out that wasn't just me. Okay, it's basically everybody that tries to learn controls. But I know that probably makes you think, I don't ever want to study this, but I highly recommend it. Because the thing about control systems is this is how you get your system to do what you want it to do. And the coolest part about it is that controls are software, right? Because they're implemented in code. They're electronics, because you're using sensors and actuators. And they're mechanical, because typically you're controlling mechanical systems. So if you're into the intersection of those 3 worlds, controls is totally for you. You would love it. There is a hump, but I promise it's worth it. All right, so that's my pitch when you go to college. All right, yes, question. Okay. Yeah. Yeah.
Sensor connection goes through something.
Yeah.
What would happen?
Yeah, so good question. So, and by the way, that was pretty much all the material that I wanted to cover. And so at this point, I just want to answer your questions. We'll start with this technical one, but please feel free to ask non-technical questions as well, okay? So your colleague's question is, suppose we have this going on where we're talking about this line where I've got my PID controller tuned, everything looks beautiful, but then a sensor gets loose, right, which happens. So that screws up this estimate, right? All of a sudden, I get like a burst of what he's talking about, noise. Like suppose, back to this, maybe the sensor's reading totally fine, and then all of a sudden I start to get all this garbage in. Well, the garbage gets fed directly into my controller. So what can happen is basically one of 2 things. Either your system's going to keep working or it's not. And not working, well, working may look like all of a sudden my sensor measurement got noisy. And so maybe I see my steering go like this, like shaking at some high rate, but I'm still kind of tracking the wall and it's okay. The worst is the sensor becomes unusable and the controller does something crazy. Okay, so this is a common thing of the controller's operating off my estimate, and if my estimate goes to junk, what do I get on my controllers? Like, what input do I compute? It's junk, right? The garbage in, garbage out thing. And so typically, what we do on very robust systems is we have to have fault protection in place so that we can actually sense when we think something like that has happened. To say, this is an invalid input. It should never be able to be above and below these ranges. I'm going to stop my vehicle. Or I'm going to just default into some like shutdown mode or whatever and flag the operator, hey, this is broken. Another one is, we didn't talk about this, but you could put something called saturation on your input to your plant. So steering, for example, right? Like, okay, so you're steering your car. You can't turn your wheels past a certain angle, right? So what do you do if your controller wants more than whatever that angle is? Yeah, just set it to the max, right? So that's a way of limiting the effect of your controller on your plant, is limit its ability to ask for illegal values. Does that answer the question? Okay, yes?
So what kind of stuff happens at JPL, and what do you like about it?
Okay, good question. So what kind of stuff happens at JPL? A lot. So we do, like I said, unmanned exploration of the solar system is our main charter. I'm in the robotics section at JPL. We're about 140 people. We work on both flight projects. So that would be NASA rovers, NASA missions, basically. But we also spend time on what's called, we call research or reimbursable work, which is for smaller sponsors like Department of Defense or even private companies will come to us and they need some custom robot, and we'll build it, or we'll do a proof of concept or whatever. I think what I really like about JPL is that like the thing I like the most are the people. So there's so many good engineers that I feel like if I let my brain be a sponge, I can just constantly absorb information. Right? It's awesome. Like, take advantage of that opportunity that you're in right now, if you're around a lot of other really smart, dedicated people, right? You all had to work hard to get to this point. So take that with you. You have a lot you can learn from each other, as well as the technical problems you get to work on, which is the second thing I like about JPL, is I'm actually not a big space nut. I'm just not. But what I really like are pushing the boundaries of engineering, and space is an excellent application for that. I also like robotic autonomy, and when we're flying stuff into space, it has to be autonomous, at least to a certain extent, based on what we were talking about earlier. So I'd say those are the things I like the most about it. Yes?
In terms of like undergraduate degrees, would you find like the area of controls to be like most in like electrical engineering?
Yeah, good question. Okay, so controls is relatively new, sort of. It really started to rise up in like the 50s and 60s. And what that means is that, and we're seeing this in robotics too, this is my personal opinion, schools haven't quite got it right yet, and how to teach something so interdisciplinary. Because like I was saying, a controller, yeah, you implement it in code. But if all you know is code, how are you gonna pick these gains? Well, to pick these gains, you need to have some intuition about the plant you're hooking it up to, and you need to be able to run tests, and you need to have some understanding of the sensors you're using. And so it's interdisciplinary by nature. So what happens at a lot of schools is they don't have a controls department. What they have are computer science department, electrical engineering department, mechanical engineering department. And then every department teaches their own controls courses. And if you're like a controls student, you might end up taking, like this happened to me in mechanical, I ended up taking a controls course in electrical, taught by an electrical professor, but it was cross-listed as a mechanical course. So it's like kind of like, they recognize that this spans these disciplines, but every school treats it a little bit differently. I don't know if that answers your question, but. So my advice would be, if you're interested in controls and if you're interested in robotics, actually it's the same. We're seeing this, like I said, with robotics right now, where a lot of schools don't have robotics degrees. What they have are mechanical engineering, electrical engineering, computer science. The school I went to has a bunch of robotics and computer science, has robotics happening in mechanical and has robotics happening in electrical, and they're a little bit siloed, which is unfortunate because what we really want is to mesh these things together. And so schools are recognizing that more and more. Like UC San Diego just opened their robotics institute as a recognition that like we need professors from lots of different backgrounds working together on this stuff. So similar with controls, I guess my advice would be, if you're interested in robotics and or you're interested in controls, just check out what the school's offering right now. See where they're at in terms of recognizing that this is an interdisciplinary field by nature. Yes?
For those engineers who work at JPL, that are more geared toward the mechanics and the technical parts of the robots that you build there, would you still have to have like a deep and complete understanding of the control systems that they use, or is like that not as necessary for those?
Yeah, another good question. So this is about like if you're just working on like mechanical hardware, right? Do you need a good understanding of control systems? I would say yes and no. Depends on what you're doing. So if you're designing like a bracket or something, like you probably don't really need to know this. But I would advocate that even if you, suppose you guys come here and you say, I don't know about robotics, I think I want to do like pretty hardcore mechanical design. I would still take at least one controls course so you have some inkling of how this stuff is working in the back of your head. And so we see that at JPL. So what we see are, there are people that do mechanical design that have pretty good understanding of control systems, which is good. They work well with with people that are writing the software, for example. It's like a good intermix of people that have more than just these siloed understandings. But then we have people that just really need to be like experts in stress analysis and thermal analysis. They probably don't have a very strong, if at all, controls background. And that's okay because they spent all their schooling learning just how to analyze bolted joints. So it kind of spans the spectrum. If you're interested in robotics, though, I think that it's necessary, and I don't even think you could really get through robotics without learning something about control systems. So if you're interested in the meshing of these things, then you do need it. Does that answer your question? Okay. Yes.
What did you do before you worked at JPL?
I'll just walk through my sort of education and career history real quick. So I think Lisa likes this story. So I graduated high school in 2006. I know I have braces, but I'm actually 29. I graduated high school in 2006. I was going to go to Virginia Tech and chose not to. I went to a different school called Rensselaer Polytech in Troy, New York. I went there for 1 year. Wasn't my jam. I left and went to UC Santa Cruz for 2 years. I did a dual degree program with UC Berkeley. So the way it worked, it's a defunct program now, but you go to UC Santa Cruz for 2 years or 3 years, and you get a degree in like arts and humanities. Mine's film and digital media. Then you transfer to UC Berkeley if your GPA is good enough, and you do whatever engineering you want. So I transferred to UC Berkeley and did mechanical engineering. So I graduated 2011 with a degree in film from Santa Cruz and a degree in mechanical engineering from Berkeley. Berkeley was when I did a senior design project where I was a controls and electronics guy for a CNC plasma cutter, which is basically a robotic device that is, it's for cutting metal. So that was super cool, got me interested in robotics. I thought I wanted to be an automotive controls engineer. I went and worked in an automotive company for the summer. I hated it. It was awful. And so I decided to not do that. I then went to Stanford for 2 weeks before I dropped out, and then lived in my mom's basement. I'm not even making this up, for about 4 months, questioning what was I doing with my life. Applying to jobs, reapplied to UC Berkeley, and got into their master's in controls. In the meantime, I picked up an internship at a robotic exoskeleton company while also working control systems as a staff research assistant at UC Berkeley. So I was still in my mom's basement, but at least I was making money. And then, so then I went back to Berkeley. I was working in a master's PhD program. I told my professor right up front, I said, I don't know if I want to do the PhD, and he said, that's fine when you complete your master's. So some schools couple them, some don't. Berkeley couples them. He said, that's fine if you don't want to do the PhD when you complete the master's. That's fine. We'll talk about that when you get there. So I did my master's in control systems. So that consisted of about 5 or 6 controls courses over 3 semesters, plus research in automotive control, which I still was learning. Like, I definitely don't want to do this. But I learned a ton about control systems. And when I graduated in December 2013 is when I got my job at JPL, and I've been there for 4.5 years working on robotics. So I think the reason I say that is because you're all smart and you all worked hard to get here. But I just want to give you one example of someone that took a very nonlinear path to get to where they are. I love what I do. And one of the reasons I love what I do is because I took the time to screw up when I was younger. And so I dropped out of Stanford. I quit this job. Like, the reason I did that is because I didn't like what I was doing, and I was still trying to pursue that thing that really got me fired up, which is this. I love this stuff, and I love coming here and talking to you guys about it. So what I would encourage you to do is, yes, there's a lot of pressure to get to like top school that you can and blah, blah, blah. That's great. But also take the time here in this experience you're having right now to just be present with what you're doing and to try to figure out, is this what you want to do with your career or not? Because if it's not, that's completely fine. I was wrong for about 4 years in what I thought I wanted. And I only found it out when I went and started doing it. So anyways, that's my background. Yes?
Pokemon Go, do you play?
I don't know. Sorry. I feel I've disappointed you. There will be, I don't even know how it works. If I played Pokemon Go, wouldn't I be taking the Pokemon from you? Or is it like not how it works? Like, doesn't it increase your odds that I don't play?
No.
It doesn't work that way? Okay.
Like if it spawns, everyone can catch it.
So there's no competition? Okay, got it.
Maybe just one more question.
One more? Yes. Yes.
How far are you in development? I guess, do you know how you're going to deploy it and how you're going to supply it?
Yeah, good question. So we're very far along the development. So the question was, where are we in the Mars helicopter development? So I'm just going to take 60 seconds, is that okay? All right, let's tell this story because I think it's very cool. So the Mars helicopter was conceived like 15 years ago, right, like when some of you were probably born. And it was by a guy who thought that you could do this. He thought that you could fly a helicopter on Mars. And many people told him that that won't work. But he kept doing the math and kept thinking, like, I think this will. So he got little pockets of money and he started putting together a prototype. And it culminated in the video you saw there, which is us flying a helicopter at 1% Earth atmosphere, which people did not think was possible. But the physics panned out. It backed up what the physics said, which is this should be possible. Now the problem is, Mars 2020, this helicopter is not part of the prime mission. What that means is we have a contract with NASA to deliver this rover, and this rover needs to achieve these objectives, which all come from science. The helicopter is not part of that. The helicopter is a tech demo. What that means is it's taking a free ride to Mars to prove a technology that isn't really necessarily beneficial to the mission, but it's beneficial to us in the long term. And so what that means is they had to be extraordinarily careful when they design that helicopter that say the deployment, that when it deploys out of the belly of this rover, that it will not, under any circumstances, impact the chances of the rover completing its prime mission. The rover needs to do its job. It's just there to drop the helicopter. It's going to drop the helicopter is going to go do its thing. It's going to take pictures. If we get the pictures, fantastic. If we don't, we're just going to keep driving the rover like we'd already planned. So that means that the people working on the helicopter had to prove over and over and over that this thing is completely robust, that it's autonomous, that it can operate on its own. So it's got its own little solar panel. To your question about power, it's going to operate for like 2 to 3 minutes a day, they think. Fly like, I think like half a kilometer a day. And if it works, it's going to give us that really good mid-range view for pictures back down to Earth so we can plan better paths for our rovers. And the main thing is demonstrate that the technology is possible. Okay, I think, are we out of time? I'll be around, so feel free to come talk to me. Thanks again for all your attention. I really appreciate it.